Hi, this is Akbar Barkesseh from Hatch, and in this presentation we are going to analysis of single phasing of three-phase induction motors, kind of a brief analysis. So first of all, what's single phasing? When a three-phase system loses a single phase on the supply system, so actually, we have a single line here explaining that the single phasing or opening conductor, single phase conductor, can happen in the point V of this motor, either at the feeder of the supply, point 1, or in the incomer, point 2, or even in the primary side of the supply transformer. So they have different impact, different type of symptoms, but this presentation is not analyzing losing supply at point 3 and 2. Of course, we're going to stop at point 2. The focus will be losing a single phase at point 1, which is the feeder of the motor. So for analysis single phasing, we need to do some sort of symmetrical component model for series type of faults, which should be good practice here to have this practice in place. Basically, when we are analyzing in a series fault, we are nominating a port or terminal between that 2 points that its open conductor happen. So point PQ, and from point PQ point of view, we have voltage between PQ, VA, VB, VC, and current between PQ, I, BI, C. So in this case, which is single phase opened, we have a VB equal to VC, basically between the ports, and equal to 0. Then we're going to the symmetrical component. Positive, negative, and 0 sequence is actually VA, VB, VC with this matrix, which is 0, 0, VB, and VC. And then we're going to get the positive sequence equal to 0 sequence equal to negative sequence equal to 1/3 of VA. Basically, it means if we have that's how we're nominating in the series fault positive sequence model, 0 sequence model, negative sequence, and 0 sequence model. It says all these voltages are equal to each other, which means they are parallel to each other. Just keep remember the point N in the series fault is not connecting to the other ports. It's not like a shunt type of analysis. So, and also keep looking at the arrows. The arrows here for positive sequence is out from the port, the other one into the voltage. So the arrow's direction is important. So again, it's repeated here. That's the model. So from what we have here, we have source and load in one side of the port, and we have motor in the other side of the port. So we have point P, you have a load and the source impedance and the source, and also motor in the other side, the PQ port, and then we have, this is for positive sequence, this is negative sequence, it is 0 sequence. We actually, if we want to reshape, this is a bit not very clear what's going on in the circuit. We actually reshaping this arrangement is like this. So basically what we have here is positive sequence in the black is coming to blue one, which is 0 sequence, and this orange one, which is negative sequence. And you see the direction of the arrows for positive here, negative here, and negative here, and 0 here. And in this arrangement, we see that the load is parallel with the source, and the motor is this side. So we're going to go to that later on. What we know about this model is, we know in the motors, because we have either delta or ungrounded star, there is infinity 0 sequence impedance. So if we put the infinity here, basically this blue circuit can be omitted. It doesn't work, if we open this put open impedance here, open point, and this blue going, and we only have the positive sequence plus the orange one negative sequence, and we can draw that like this. So no blue one. And from this, we have this boundary condition that the positive sequence current is equal to negative sequence current in opposite direction. So I1 equal to minus I2, and zero sequence is 0. So then we have AA, AB, AC. For the motor is actually this matrix is I0, I1, I2. We know that I0 is 0, I1 is I1, and I2 is minus I1 because of the model. So if we put all this together, then we reach to this, that the magnitude of IB is equal to magnitude of IC is equal to I1 multiplied by a square root of 3. That's very important. So I'm just going to have some sort of a little stop in the other scenario that we have open circuit in the incomer. So this one that I just repeated the previous one here. So we have the previous one, and we reached to just a simple equation that motor current phase A is 0 and B and C is this. But here, what's the difference between this and this? In this one, the load is parallel with the motor. It's not parallel with the source. So if we compare these two circuits to each other, we see that for the load is going to be parallel with the motor, and the load which it is here is the load is parallel with the source. Now load is parallel with the motor. So we have this sort of arrangement for 3 of them. And interesting that, and I did all sorts of calculation here to get all of this value based on I1. Imagine that we have a circuit here, all values are known, so we can calculate I1. Then from I1, we have phase A, this big value of impedance multiplied by I1, IB if this one multiplied by I1, and IC is this one, the motor. Just keep in mind that they are motor current. So I'm not interested of the phase current of this point. I'm interested the phase current of the motor here. So what we have here, I have I1 motor here, I2 of the motor in this branch, and I0, which is 0 for the motor, is here. But keep in mind, although the motor has 0 sequence current equal to 0, but here we have 0 sequence current because we have a 0 sequence current in place. And it's different. And also remember that here the current in the phase A of the motor is not 0. And it has some value due to existence of the load, and basically it means although the phase A been disconnected from here, but the phase A of the motor have some sort of interaction with the load in this area. I'm not going to go further in this, but I just wanted to say different approaches and maybe getting different values. So we are in this simple one that the I motor IA phase A is 0, B and C equal to a square 3 times of positive sequence current or negative sequence. Then we're going to the simplifying circuit for analysis. So we have basically this circuit, and if we want to simplify that, one of good, to get some sort of idea and feeling about single phasing, we can assume that the load is infinity, is actually no load, the impedance of the load, and also with a good assumption, we can actually assume that the source impedances are 0. And it's not very unacceptable or very unrealistic assumption, because normally we're maintaining voltage at the buses by transformer tabs. So that is a sort of controlling voltage, is sort of zero value, kind of infinite, but kind of. Otherwise, if you are going to study voltage drop things, that's a different thing. But for us, we can say that they are zero. So it's very, very simplified that in this case to adjust a source voltage in per unit in phase, and we have positive sequence in series with the zero sequence impedance of the motor. So the I1 is equal to the voltage of the per unit voltage of the system in phase divided by zero sequence plus positive sequence. So if we actually get zero sequence positive sequence impedance out, then we have this value E divided by positive sequence impedance multiplied by this value. So we know that this one is the nominal motor nominal current. So nominal current of motor is not about the voltage divided by positive sequence impedance. But so we see as a factor here is multiplying by nominal current. So we are interested to know what's the factor. This factor is related on the ratio between negative sequence and positive sequence. If actually we introduce n, opposite of this ratio, positive to negative sequence, then we can write it down that this the motor current is basically n multiply a squared 3. So we are interested to know the whole value of this ratio. What's going to happen? So before we're going to repeat that later on, but here we're going to talk about the electrical circuit of the induction motor, three-phase induction motor, just reviewing that. So we know that for induction motor we have a stator winding and leakage, and the leakage of rotor, and the rotor divided by slip, and we have the magnetization branch, which can assume is open circuit or infinity. So that's typical in all books, you can find that. And then we have for a starting we can put S equal to 1. So we have this one just S equal to 1. That's for a starting S equal to 1. So what's going to be the negative sequence equivalent of the induction motor? So in the negative sequence, one of the easy way is when we're writing down the slip equation, we should put the minus of omega s for negative sequence, because it's actually creating the synchronous speed in opposite direction. So if we, instead of putting omega s minus omega r divided by omega s, we put in minus omega s minus omega r minus omega s. So basically we have omega s plus omega r divided by omega s. And if we wanted to create the positive sequence, a slip from that, it basically is equal to 2 minus this, which is 2 minus s. So is equal the motor equivalent circuit for negative sequence is exactly like positive sequence, except for this R divided by S, you have R divided by 2 minus S. And interesting that if you put S equal to 1 for a starting, is exactly with the similar to the positive sequence one. So what is one to say that the starting equivalent for positive and negative sequence are equal to each other, and when the speed change, the differences between positive sequence impedances will appear. So quickly, when going to the negative sequence, we want to get some sort of idea about the magnitude of the currents. So we have this negative sequence circuit. Then basically for the operating S around the nominal value, which is this the S around this area, they are very small s. They are around 0.04 to 0.01. So such a small s, R divided by 2 minus s, basically you can assume is equal to R divided by rho 2. So this one we can ignore S for the speed around the nominal speed. So we can get this R equal, RR divided by 2. Another thing we can assume that generally in the motor, the rotor resistance is squirrel cage rotor resistance are much smaller than stator resistance, which are all these windings. So in this case, this R rotor resistance divided by 2 plus stator resistance, we can actually divide it by 2. We can actually even say equal to R divided R plus RS. So what's the benefit of this? Then we can say this model is equal to this model, approximately. So what is this model? This is the starting of impedance of the motor. So what does it want to say? Approximately that around the typical speed, the negative sequence impedance of the motor is almost the starting impedance of the motor. So then we back to that equation that we were after. What is this value? So now from the around nominal speed, this ratio, positive to negative, is approximately positive to a starting. And positive to a starting is inverse of a starting current of a starting current divided by nominal current. So for a typical value of starting to the nominal of 6, the starting current of 6 times of nominal current is very typical. Then it means n equal to 6. If we put 6 here, then we have the actual current in the motor is almost 50% overload, which is a severe overload for motor when it's single phase. That's one of the facts. We're going further. Now we're going to analyzing the torque. So before that, so this is the model of the system, positive and negative in series. So we are actually putting the real positive negative values here in series. Then just for remember, people doesn't know, if you want to take out the R as a real value from this one. So R divided by S could be R divided by S plus minus IR. So and then we're taking out the rotor resistance and say this one is a rotor resistance plus. So basically instead of this, we have rotor resistance plus this value, and instead of this, we have rotor resistance plus this value, which is opposite sign of that, but different value. So what's important? Why they are important? Then what about the couple loss? So couple loss in single phasing basically is 3 times, because this is a single phase model, in symmetrical component. In symmetrical component, we all assume the system is 3-phase. So 3-phase component and is a positive sequence and negative sequence are the same. So we have here this rotor and stator resistance. We have 2 of them multiplied by 3 because of 3-phase, and I1 square. For nominal system, we don't have 2 of these, we only have this one. So we have 3 times of R stator plus R rotor and the nominal current of the motor. So in this case, if we put the values instead of I1, we put approximately 1.5 times because of that 6 times typical value that we know. Then we put here, then at the end we're reaching to 1.5. It means 50% more almost the heat is going to be generated inside the winding of the stator. And in addition to that, cannot be captured by this model is eddy current, which is huge in the rotor. So we have excessive heat in the enclosure of the motor. Now it's going to a bit quick investigating about the torque and the speed. So assume speed is not changed after single phasing. Is not correct, will be discussed in the next slide. So we're going to see is not correct, but let's say the speed is not going to change. So I mean the S value is the same. So electric torque when it's single phase is basically these two elements that we made it separately. This one multiplied by I1 square. Basically, this not torque is power, but doesn't matter. So, and this one is for nominal type, which is just this one, multiplying by rotor, this value multiplying by I square of the nominal. But what sort of assumption is, basically this is the positive sequence torque, and this is the negative sequence torque in the minus degree. But this value is much around the nominal speed. This value is much less than this value. So imagine if it's 0.04 s, then this value is a bit huge. It's going to be 33, and 2 minus that is 0.5. So we can actually ignore that one, which is here. That 1 point is much bigger than this one. The negative, also that we know that negative sequence torque will opposite the positive sequence, and we see the minus sign here, but the magnitude is much less around the nominal speed. So we can just ignore it and put 1s. So this equation then will be simplified only to positive sequence square to nominal motor square. And for positive sequence, again for that typical value which we can found for 6 times of the starting current, 1.5 times of the nominal current, and then divided by the square root of 3, because the equation between I1 and real motor phase current, we reaching to this value, some sort of typical value, 0.74. What does it want to say? It wants to say that electric torque of the motor in the single phasing will reduced. Reduction in electric torque means reduction in speed. We're going to the next slide to explain. This is the torque speed characteristic of the induction motor in normal condition. So what is want to say 25%? So it used to be here, for example. Now is 25% less. So when you say 25% less, it means this curve is changed. It's like this dash line curve. It's like this dash line curve now. So for this for the nominal point, it has dropped. It drops the torque. It means this we now have a different curve like this. We don't know what it looks like, but we know it's like something like this. But we definitely know that hit is 0. We're not going to have any value in the 0 when the single phase motor becomes two phase. I mean, 3-phase motor becomes single phased, because in the starting point there are two magnetic fields opposite each other, and the rotor cannot follow any of them. So we have exactly zero electric torque in here. So then we now see, I just deliberately put 2 types of mechanical load here. One type of mechanical load, which is kind of fans, that you see previously is hit the curve in here, and the nominal speed was here. Now the curve is changed, and it hits the load in this point. So this is the nominal, the new speed of the motor. So we have that much drop in the motor, and the motor keep rotating. But imagine that instead of fans like this, we have like thing like a conveyor, a fixed torque type of the mechanical load. And now this curve cannot hit this one, or this one is not a stable point. So what does it mean? When the electrical torque is less than mechanical torque, means stalling. So it dropped the speed straight away to here. Means the motor is going to be lock rotor. So that's a question here. We cannot definitely say when a single phase happen in three-phase motor is always keep rotating with some sort of overload. It could be stalled and completely stop. So different, it depends on this. If we actually model and calculate exactly what this curve looks like, we can say, in combination with the mechanical torque, we can say either it reached to the new point and keep rotating or going to the stall position. So depending on the torque speed characteristic of the mechanical load during single phasing, a motor either drops speed and keep rotating or dropping speed until complete stalling. Just before, we said about the stalling of the motor in the single phasing. Just wanted to say when it's stalled, it doesn't draw the exactly starting current or lock rotor current of nominal current. It has a bit different because we have a positive and negative sequence in series. We know in the starting, in the lock rotor position, both of them are equal to each other, equal to a starting impedance. So we have 2 times of a starting impedance. So I1 is equal half of the starting current. But the motor is draw square 3 times of I1. So it's about a square root of 3 divided by 2, so it's 0.866 times of IN. So just keep remember that this starting current is not exactly same as the nominal starting current. For example, if it's a 6 times nominal current for a starting, then it draw 5.42 times. So that's all about this. So we're going to the conclusion. Loss of single phase in three-phase system can be happen mostly due to single phase fuse operation. Single phasing can be in the motor feeder, switchboard, incomer, or primary side of supply transformer. We see that at different point could be single phase, and they have different symptoms. The fault is a series fault type, so within the symmetrical component, we are going to the investigating series fault. And then depending on the torque speed characteristics of the mechanical load, either motor drop speed and keep rotating with significant overloading and excessive heat stress inside motor compartment, or will drop speed until full stalling and will consume 0.866 of nominal starting current. So that's all for this, and I hope that it helped for you. Thank you very much, and thank you very much for watching.